Hi everyone, welcome back. In this lecture video, our learning goal will be to describe the energy levels, sublevels, and orbitals for the electrons in an atom. And you can see here a beautiful rainbow, which forms when light energy passes through water droplets. So let's talk about the electromagnetic radiation. We experience electromagnetic radiation in different forms, such as light, the colors of the rainbow that you saw in the previous slide, and X-rays. Those are just a few examples. Electromagnetic radiation consists of energy particles that move as waves of energy. If you've ever heard of the wave-particle duality of light, that's referring to electromagnetic radiation that behaves not only as particles, but also as waves. We won't cover that in this class, that's quantum mechanics, but having a brief introduction into this wave-particle duality will help us understand where electrons are probably located in an atom. And notice how I was intentional with using the word probably, because we never know the exact position of an electron at any time, but we have a good probability guess. The distance between the peaks of a wave, of waves, is called wavelength. And then just some other things to make note of. High energy radiation has shorter wavelengths, and low energy radiation has longer wavelengths. And so the energy is equal to hc over lambda. E is energy, h is Planck's constant, c is the speed of light, and lambda is wavelength. And so the way I always remember the relationship between energy and wavelength is through this formula. So what that means is energy is equal to 1 over lambda. If we just assume hc is 1, it's not, because there are different values here, but just looking at the relationship between energy and wavelength, and we can see that they have an inverse relationship. So the higher the wavelength, the higher the energy value, the lower the wavelength. The smaller the energy value, the longer the wavelength. And so they're just inversely related. Now, when light from a heated element passes through a prism, it separates into distinct lines of color, separated by dark areas, and this is called the atomic spectrum. And the reason why we're going through this is because each element has its own unique atomic spectrum. It's like its unique fingerprint pattern. So for example, if I take a sample of barium and I light it on fire, and the light passes through a slit, so this is inside a dark box, and then the light given off when I'm burning the barium, it's green actually, the light goes through that slit and then interacts with the prism, and then that separates it into distinct lines of color, and this is an atomic spectrum unique to barium. So once again, atomic spectrum is like a fingerprint pattern for each element. And so because of that, this gives us idea, because usually we were thinking, oh, light's a wavelength, right? Like we just saw in the previous slide. But then when it passes through a prism, it has distinct lines. So that speaks to the energy of that light. And this is what's leading us to understand electron energy levels. So the lines in an atomic spectrum are associated with the changes in energies of the electrons, because every element has a different number of electrons. So it's all going to come back down to the electrons. And in an atom, each electron has specific energy known as an energy level. So we have distinct energy levels, and they are going to be assigned whole numbers. So whole number integers, and we call these principal quantum numbers. So we always start with n, so principal quantum number n. We have n equals 1, n equals 2, n equals 3, so on and so forth. And every time, we go up an energy level, that increases in energy as the value of n increases. And something also important to recognize is that electrons that are in higher energy levels, such as n equals 3, are farther away from the nucleus. So electrons in the energy level n equals 1 are close to the nucleus. And I always like to personify my electrons. So I say those electrons in n equals 1 are really happy because the nucleus is positively charged because it has protons and neutrons. The protons make it positively charged. And electrons are negatively charged. And we learned in a previous video that in chemistry, opposites are attracted to each other, right? Those opposite charges really like each other. So electrons closer to the nucleus are very happy there because they're closer to that positive core. Now, the energy of an electron is quantized. And what that means is that electrons can have only specific energy values. So the electromagnetic spectrum shows an arrangement of the wavelengths of electromagnetic radiation. And the only one that we can see physically is the visible range. And that's from 400 to 700 nanometers. So when you see nm, that is nanometers. It's really small. 1 times 10 to the negative 9th meters is a nanometer. And so let's just look at this electromagnetic spectrum. So just from low energy to high energy as we go across. And you can see here wavelength, in this case, is in meters. Typically, when we discuss wavelengths, though, we're usually using nanometers, but you could use any metric system units there, meters, nanometers, centimeters if you want. So that's the units used here. And then frequency is here as well. We won't speak too much about frequency in this class, but if you take a physics class, you'll definitely dive in deeper to the energy equation I just showed you and frequency and how that relates to wavelength. But all I want to just explain here once again is the relationship between energy and wavelength. And for example, radio waves, those are long wavelengths, whereas gamma rays are really short wavelengths, right? Radio waves are long and therefore have lower energy. They're inversely related, the wavelength and the energy, like we saw in the previous formula. Now, if we're looking at gamma rays, those are very dangerous for our health, right? Those have very short wavelengths, but high energy. So very short wavelength, but high energy, that inverse relationship between wavelength and energy. So let's come back talking about those electrons. So electrons with the same energy are grouped in the same energy level. And I like this picture here of a bookshelf, right? So we will treat n equals 1 as the lowest shelf. And we will put, books in there. Those just represent your electrons. So we will always fill up the lower energy level first before we move up to a higher energy level, n equals 2. And then just as a reminder, those energy levels are assigned values called principal quantum numbers. And that's quantized, so it's like discrete energy levels, and we use whole numbers, starting with n equals 1. There's no n equals 0. It starts with n equals 1, and then moves up 1, 2, 3, 4, and 5. Now, if we apply energy Then electrons can move to a higher energy level when they absorb the energy. So this electron here, it absorbed energy and it jumped up to another energy level. But eventually, electrons want to relax back down to where they started. And when they do that, low energy light is emitted. This is what happens when you go see fireworks. What happens is those elements in the fireworks, their electrons get excited when the explosion happens, right? And then when the firework goes off, but eventually the electrons in the element relax back down and light energy is given off. So the barium you saw earlier gives off a green color. Strontium gives off a red color. And what you're observing when you go see fireworks is just those electrons getting excited. And when they relax back down to their original energy level, they're giving off light. And they're giving off light in the visible region. So that's why we see the colors. The energy emitted or absorbed is equal to the differences between the two energy levels. And this just follows with the law of conservation of energy. Energy cannot be created nor destroyed. And so the energy emitted, so that's this light coming off, emission is just coming off there, or absorbed is equal to the difference between the two energy levels. So let's talk about sublevels. It is the arrangement of electrons that determines the physical and chemical properties of an element. That's where we're all headed down here. I'm giving you a very short overview of wave particle duality, quantum mechanics, and all these energy levels. But in the end, for this class, we're really focusing on how that all helps us understand the arrangement of electrons. And the reason why we want to learn that is because understanding the arrangement of an electrons in an element helps us understand the physical and chemical properties of that element. Now, I'm just going to go through some more definitions here, and then eventually we're going to get into those orbitals pretty soon. But coming back to this, each energy level consists of one or more sublevels. The sublevels are going to be S, P, D, and F. And the number of sublevels in an energy level is equal to the principal quantum number N of that energy level. And I'm going to show you that in the next slide. I'll have a nice figure to explain that. And the order of the sublevels in an energy level is S, P, D, F. So S is lower in energy than a P sublevel, which is lower in energy than a D sublevel, which is lower in energy than an F sublevel. All right, so this is going to help us eventually, like I said, understand the arrangement of an electrons in an element. We will always start with electrons in N equals 1, and there's only one sublevel, and that's the S sublevel. And once we fill the 1s, we will move up to N equals 2, which has two sublevels. It has S and it has the P sublevel. Now for the S orbital, you only have one S orbital in a sublevel, but for the P, we'll learn that you have 3 P orbitals in a P sublevel. For N equals 3, there are 3 sublevels, S, P, D. Once again, 1s, 3p, but for the D, we have 5 D orbitals in the D sublevel. N equals 4, we have 4 sublevels, S, P, D, and F. As you can see, everything looks the same as P and D, but F has 1, 2, 3, 4, 5, 6, 7 orbitals in the F sublevel. So let's talk a little bit more deeply about S orbitals. Well, first of all, the word orbital means that there's a 3-dimensional volume in which electrons have a high probability of being found. So we won't go through what's called the Heisenberg uncertainty principle, but all I will say is that we do not know the exact location of an electron at any point in time, and it is a probability distribution map of finding it. So it's the likelihood of finding that electron is in this three-dimensional space called an orbital. So if I tell you an electron's located in an s orbital, that means that electron is located in what appears to be like a sphere, right? And this is actually right here, this is an electron cloud of an s orbital that represents the highest probability of finding the s electron. So this is done theoretically through lots of calculations to develop this cloud and the probability of finding an electron there. And what I also just want to highlight here is that depending on what energy level you are, changes how big that orbital is. So notice how the 1s orbital is spherical, but smaller than the 2s orbital, and the 2s orbital is smaller than the 3s orbital. So as you increase in energy level, the size of the orbitals also increases. And remember, orbitals are the likelihood of finding an electron. So electrons that are in the 3s orbital are farther away from the nucleus. The nucleus is in the center of these Cartesian coordinates here. And so if it's a 3s orbital, 3s electron, then that electron's a lot farther from the nucleus. Whereas a 1s electron is close to the nucleus. Like I said earlier, it's very happy the closer it is. P orbitals, remember there are 3 p orbitals in a p sublevel, and it starts with n equals 2. And p orbitals look like balloons. I'll show you on the next slide. It looks like a balloon tied in the middle, and each can hold a maximum of 2 electrons, just like the s orbitals. And the 3p orbitals are arranged perpendicular to each other along the x, y, and z axis around the nucleus. Although for this class, I'm less concerned about you drawing what the orbitals look like. I just want you to have an understanding, a basic understanding of what they look like, but you won't be drawing them for me. But basically, there are 3 p orbitals in a p sublevel. Each can hold up to 2. So therefore, you can hold up to 6 electrons in the p sublevel. And you can see here how they all line up. Like if this is an atom and the atom contains these 2 p orbitals, they all line up. It looks kind of like a flower where the center is the nucleus. And then d orbitals, there are 5 d orbitals, and they have these unique shapes, and these are their names: dxy, dyz, dyxz, dx squared minus y squared, and dz squared. And once again, you're not going to be expected to draw these orbitals, but just understand that you can fit up to 2 electrons in each orbital. So because there's 5 d orbitals in a d sublevel, you could fit up to 10 electrons. 5 times 2 is 10. All right, now we're getting closer and closer to being able to understand how electrons fill these orbitals. Let's talk about orbital capacity and electron spin. So the Pauli exclusion principle states that each orbital can hold a maximum of 2 electrons. That's important. Electrons in the same orbital repel each other, and electrons in the same orbital must have their magnetic spins cancel out. Once again, this idea of magnetic spin is a quantum mechanical principle, which we're not covering in this class. But all you need to recognize and remember is that when we eventually draw electrons in the boxes, then one electron, the arrow, this represents an electron, and the arrow is pointing up. And if it's in the same box, the other electron has to be pointing down. And this just represents this quantum mechanical principle called magnetic spin. And we always say with that they have opposite spins. But once again, that's not critical to your understanding of what we're covering in this class. But if you go on to take physics or physical chemistry, you'll dive in deeper into quantum mechanics and how this is all determined in a greater detail than I'm able to cover here. Now let's talk about number of electrons in the sublevels. I've alluded to that already, but I want to review over this. So each s sublevel only has 1 orbital. and it can hold up to 2 electrons. So for S, we have a maximum of 2 electrons. For P, we can hold up, because there's 3 orbitals, we can hold up to 6 electrons. Each orbital holds 2, so 3 times 2 is 6. For the D sublevel, it has 5 orbitals. It can hold up to 10 electrons because each orbital holds 2 electrons, so 5 times 2 is 10. For the F sublevel, it has 7 orbitals, and it can hold up to 2 electrons in each orbital, so 7 times 2 is 14. So the F sublevel can hold up to 14 electrons. We're primarily going to focus on S, P, and D. When we talk about F, that's usually the lanthanide and actinide series down here. We will not be working with those types of elements in this class. So this table is a nice summary to kind of look through. For example, based on energy level, N equals 1, 2, 3, and 4. Remember, the number of sublevels is equal to the energy level. And the type of sublevel, you always start with S. And this one only has 1 S. But if you have 2, then we have 2S, 2P. If we have 3 sublevels, then we have SPD, so 3S, 3P, 3D. And if we have 4 sublevels, we have SPD and F. So 4S, 4P, 4D, 4F. And then you can see that the number of orbitals in that sublevel. So for any S, you notice there's only 1, but for P, there's 3, for D, there's 5, for F, there's 7. And then the maximum number of electrons, you just take this number, multiply by 2 to get the maximum number of electrons. And then these were just added up. So for elements in N equals 4, we can hold up to 32 electrons. N equals 3, up to 18 electrons. N equals 2, 8. And for N equals 1, 2 electrons. All right, so go ahead, pause the video, try the study check on your own, and then come back and check your work with me. So which of the following elements are likely to have electrons in the 3p sublevel? Is it carbon, silicon, oxygen, or AS? Let's look at what AS is. AS is arsenic. I thought it was arsenic, but I wanted to double check there. So have your periodic table handy. So with this one, we have carbon, silicon, oxygen, arsenic. And we're asked which of the following elements are likely to have electrons in the 3p sublevel. So if we look at the periodic table, the way you can determine energy levels is through the period numbers. And so this will kind of give you a clue to your principal quantum number, N. So this is N equals 1, N equals 2, N equals 3, N equals 4, 5, 6, and 7. And in a later video, I'm going to teach you how to use the periodic table, combine the knowledge of the theory that we just learned in this video to doing what's called electron configuration. That's where we're headed. That's the end goal for this type of work here. But for right now, the question's asking us which of the following elements are likely to have electrons in the 3p sublevel. So the elements have to fall along somewhere in N equals 3, at least, if not higher, because then we'll learn later on, like iron will have electrons in the 3p. We will also learn in a later video that this is the S block. This is what's called the D block. This is the P block, and this is the F block. And so if I'm looking at, for example, carbon's located in N equals 2. So it will not have electrons in the 3p. This is going to be the 3p sublevel here. So carbon won't count. And it also asked about oxygen. Oxygen won't count either because it's in the same N equals 2. But silicon will. Silicon is in the 3p, so 3s, 3p. So it will have electrons in the 3p sublevel. And arsenic is in 4p. And what we will learn is that, anything before it has, it will also have electrons in the 3p. And like I said, in a later video, when we do electron configuration, I'm sure this will make a little bit more sense. But for right now, we're just introducing our understanding of where electrons are located, and what type of orbitals, and which sublevels, etc. So like we said, for carbon, that's an n equals 2. So it cannot have electrons in the 3p sublevel. Silicon is an n equals 3 and does have 3p electrons. So yes, it will have electrons in the 3p sublevel. Oxygen is an n equals 2. So once again, it cannot have electrons in the 3p sublevel. And arsenic was in an n equals 4. So yes, like it will learn later on, like even if it's an equals 4, it still has electrons in n equals 3 because we have to fill up that row first before we move on to n equals 4. So yes, it will have electrons in the 3p sublevel. All right, thank you for watching. And as always, email me with any questions.